are looking at section 3.9. It's called related rates. And it really, just when you thought it couldn't get any, worse than today, of course, how do we make math worse?
Apply it.
Yes, let's apply it. Let's have some word problems. That's right. That's what we're going to do today. We're going to have related rate word problems. But you already know how to do this, okay? Because it's really just implicit differentiation. But instead of instead of having the expression like in terms of x and y, and you're differentiating with respect to x, and so like whenever you had an x, the derivative of x was just dx dx. It was just 1. You didn't have a dx dx. You didn't write that. Well, now say if we have an x and a y, we're going to differentiate with respect to t. Time is most of the time related rates has to do with time. And so when we take, if it was x squared in the equation, when we take that derivative implicitly with respect to t, it would be 2x dx dt. Does that make sense? So that's kind of what's going to happen, but it does get painful because you have to come up with a lot of equations, which is never any fun. But we'll walk through it, and it'll be good. You'll have a blast.
All right.
I know. It's going to be fun. All right, related rates. In this section, we deal with the problem of finding a rate you cannot measure easily from some other rates that you can. To solve related rate questions, you write an equation that relates the variables involved and differentiate to get an equation that relates the rate you seek to the rates you know. Sorry, hold on. The MCC people aren't processing. Is that better? Okay. After you have done this, you plug in the given information to find the final answer. So one of the mistakes that can occur when you're working these types of problems, related rates problems, is that you plug in too soon. You plug in the information that they give you too soon. All right, so you really want to do that as your last step. That's why I was trying to warn you. All right, so let's just knock one out. It says the radius r and the height of a right circular cylinder are related to the cylinder's volume, V, by the formula V equals pi r squared h. You've got a cylinder. And remember, the volume, what you do, this is kind of fun, if this is r and this is h, you just imagine infinitely many little circles stacked on top of each other. And if you added up their area, that would be the volume. It's an integral thought that you'll have later, but that's how they get remember, the area of a circle is pi r squared, and then you just multiply it by the height of the thing. And that's where that formula comes from. Okay, and so it says, how is dv dt related to dh dt if r is constant? Okay, so you need to think of r as a fixed number. So it can be 8 or 12 or whatever. When you're differentiating, you need to remember that it's a fixed number. So if you have v equals pi r squared h, this is a number, like it's 25 pi or something like that. So when you went to find dv dt, the derivative of v with respect to time, you would just differentiate this term, which is like 25 pi h. Well, if it were 25 pi x and you were finding the derivative of x with respect to time, you would say 25 pi and then dx dt. Well, here we're going to say 25 pi dh dt, but we don't know what the number is. Our r squared represents my 25 there. It's just a constant. So this is pi r squared, and because that's just your constant, and the derivative of h with respect to time is dh dt. Okay? Now it says, how is dv dt related to dr dt if h is constant? So now we're going to think of h as the number. Okay, so you're still going to have v equals pi r squared h, but dv dt, well, this h tags along with the pi because it's constant. Okay, so you could say pi h. Then you go ahead and differentiate r squared like it's an x squared. How do you differentiate that? 2r, but you're differentiating with respect to time, so you have to say dr dt. There's some implicit stuff going on there. Okay? And so you might clean it up because we normally like to put the 2 first. So 2 pi r h or hr dr dt. However you want to put your letters is fine. Okay? Now, what about if neither h nor r, or r nor h, are constant? Well, if that's true, if they are changing as well, then you actually have a product rule. You have two different things. You have a u and a v. Okay? So, differentiating with respect to t, your u is pi r squared, so your u prime will be 2 pi r dr dt. Make sense? And your v is h, so what is v prime? 1 d h dt. All right? It's dh dt. Okay? Does that make sense? The derivative of h is just 1, but you have to say that you're differentiating with respect to time. All right, now, the product rule is u times v prime plus v times u prime. So, dv dt will be equal to u, which is pi r squared, times v prime, which is dh dt, plus v, which is h, times u prime, which is 2 pi r dr dt. All right? So that was not so bad. What do you think? Okay? Let's see if we can make one a little bit more exciting. Guess what law I'm talking about in number 2? Whose law?
Is it Ohm's?
It is, so you have to go. It was a joke. Wasn't very good. Okay. All right, so here's my formula, V equals IR. And you're asked, it says, let's read the problem. It says the voltage V is in volts, and current I in amperes, and resistance R in ohms of an electric circuit is related with the equation, which is called Ohm's law. It's VIR, V equals IR. Suppose that V is increasing at a rate of 1 volt per second. All right, so they gave you dV dt, while I is decreasing at the rate of 1/3 amp per second. So that is di dt. And notice that it would be negative. Okay, it says let t denote the time in seconds. All right, now the first question is, what is the value of dV dt? Well, that is right there. dV dt is the change in the voltage with respect to time. It's just a rate. It's increasing at 1 volt per second. Gotta like these questions. All right, what is the value of di dt? Di dt is decreasing. Notice that it is decreasing. So decreasing, mathematically, we would put a negative there. So di dt is equal to negative 1/3 amps per second. All right, what equation relates dr dt to dV dt and di dt? Well, let's go ahead and see. Start with V. V is equal to I times R. Start with what it's equal to. And let's solve this for R. What would that be? If we solved it for R, we would have V divided by I is equal to R. Do y'all agree with that? Now, when you're dividing by a single term in the denominator, and you know the chain rule, it's sometimes easier to use the product rule to do the division instead of having to do the quotient rule if you recognize that you could write this as V times I to the negative 1 power. Do y'all agree with that? And don't you think sometimes the product rule is just easier? Okay, so the product rule, if we want dr dt then, remember the product rule is u, which is the first, times the derivative of the second. So that's going to be V times the derivative of I to the negative 1 is negative I to the negative 2 di dt. Does that make sense? plus the second, which is the v, I to the negative 1 times the derivative of v. What is the derivative of v?
dv.
There it is, dv dt. So I just used the product rule, but I was kind of did it without writing the u and the v. Are y'all okay? All right, and so then dr dt kind of simplifies as negative v over I squared di dt plus 1 over I dv dt. Okay, so there's our formula for the change in the a resistance with respect to time in terms of the voltage and the amperes. Okay, so now it says find the rate at which R is changing. So they're looking for dr dt when V is 12, so you'll put 12 in for V. I is 2, you'll put 2 in for I, and and they had already given us di dt and dv dt in the original problem. Okay? So di dt was given to be negative 1/3, and dv dt was given to be something else, 1 volt per second. So we're just going to take this formula, dr dt, which is equal to negative v over I squared di dt plus 1 over I dv dt, and put in our different pieces. So my v, this is going to be negative 12 over I, which is 2 squared, times di dt, which is negative 1/3, plus 1 over I, which will be 1 over 2, times dv dt, which is 1. Is everybody okay with what I did where? Okay, and so then this is equal to negative 12 over 4 is 3, so that's positive 1. 1 plus 1/2, or 3/2. Oh, and I was a bad scientist. What do bad scientists do?
They don't put their units.
Oh, you go, boy. That's right. So, but in my notes, I put all my units, but I'm really bad. Okay, so let me try this again. I guess now, since I'm going to be punished for not putting my units, so I'm going to write the whole thing over again because I was bad. All right, I should write this as negative 12 volts over I squared, which is 2 amps squared, times di dt, negative 1/3 amp per second, plus 1 over I, what was I? 2 amps, times dv dt, which was 1 volt per second. And the reason you should put your units is because hopefully if you did the problem right, your units should all cancel to be in the right units in the end. And voltage is measured in volt amps per second, volt per amp per second, which is an ohm per second. Okay, a volt per an amp is an ohm. So if you notice, you've got amps squared here and you've got an amp there. So you are going to have volt amps per second, and then here volt amps per second. You know, it's going to work. So you do get, back to the final answer, you get 1 volt amp per second, and then plus 1/2 volt amp per second. And so finally, you do get 3 volt amps per second, which is 3 ohms per second. Okay, so I definitely need to model correct scientific behavior there, which is to use your units. I'm sorry I didn't do that.
3/2.
I'm falling apart. I need to drink some coffee. Okay. Strategy. What strategy should you use when solving related rate questions. I think it's a good idea to find someone else who really likes science and just ask them to do the problem for you. It's a good strategy. I don't know. All right, now what you should do, you should always breathe and you should be like, I love these problems. They're so much fun because I get to show you how much I know. And first, I'm going to draw a picture. Now, often students get stuck in the draw a picture, and they're really good pictures, hoping that the teacher will give them some credit for a nice artistic representation. So draw a picture and figure out what you know and what you don't. Talk yourself through. Really, the first strategy should be read the problem about 6 times. Read it until you really process, and that'll help you figure out what you know and what you don't. Strategy 2 is to write down any numerical information. The third thing you should do is write down what you are asked for. The fourth thing you should do is write an equation that relates all the variables. This is the hard one. Right? Because you have to come up with the equation. An equation that relates all the variables. And then you are going to differentiate that equation with respect to time. Notice, no numbers have been plugged in. All right, you're doing everything with letters. Finally, the last thing you do is evaluate with the given values. Okay? And then I said, I recommend reading the examples in the text for section 3.9, page 234 to 236. I will do some now, just breathe. Okay. All right, so one of the best ways to get better at these is to work examples. And so I almost always try not to work the examples that are given. And you know how the textbook has like a lecture section where there's notes in it and then there's exercises? And I try never to do those problems that are in that part of the book because I'm expecting that you're reading it when you need to. And so you can read even more examples if you go to that section. Okay, so that would be a wealth of examples that you could write down and think about. That would be very helpful. All right, here's an easy one. When a circular plate of metal is heated in an oven, its radius increases at a rate of 0.01 centimeters per minute. At what rate is the plate's area increasing when the radius is 50 centimeters? Okay, so the first thing you do is draw a picture and figure out what you know and what you don't know. So we've got a circular plate, and it's in an oven, and its radius is increasing at a rate of 0.01 centimeters per minute. So it's got a radius, r, and we know that the dr dt is given to be 0.01 centimeters per minute. Do y'all agree? Now it says, at what rate is the plate's area increasing? So that is what they're looking for. We want dA dt when r is equal to 50 centimeters. Okay? Now we're not going to plug in any of the numbers until we get going on there. So I sort of did steps 2 and 3 because I told you what we're asked for, dA dt, and I told you what we are given. So now we're on step 4. Write an equation that relates all the variables. Does anybody know an equation that maybe could help us here?
Pi r squared.
Yeah, the area of a circle, right? So we know that area is equal to pi r squared. Okay? Now we can differentiate this formula with respect to time. So dA dt will be equal to, what's that derivative going to be? Robinson? I know. You're going to have to do it for me. Can you tell me? One of y'all. Quit talking. She's talking. Green shirt girl. Hit the girl in the pink with the black. Yes. Slap her. Say, how do I do this? Don't slap her. Hey. I want you to try and tell me the derivative of this problem with respect to time.
We have no clue.
Oh my God, what are you doing? You're so mean. You don't think I can see you? Why aren't you paying attention?
Well, we're sure, but we think it might be 2 pi r.
Well, I think you're wrong, okay? Because this whole thing's about related rates, and you have to have a drdt on there. You know, I'm just not talking to you. Go mute yourself. Okay, so this is 2 pi r dr dt. The whole idea here, Robinson, is that we have this new idea, which is that we are differentiating implicitly with respect to time. And so we pop it here. Okay. All right, whatever. Okay, now Robinson.
It was our bad. We just forgot the related rate part.
Yeah, whatever. Help me finish this problem up. They're sorry. You guys, I need the answer, so plug in the correct parts and finish it up for me. It's not that hard. You can probably figure it out. Unmute and talk me through it.
Wait, don't. No. 0.01. Is that a 01? Yeah. Times 2 pi r.
That's easy.
R. And r is 50.
There it is.
And then times the 0.01.
Oh, I got to put a centimeters here and a 0.01 centimeters per minute there, right? Okay, and if we multiply that out,
100 pi. Well, more than that.
this is 1/100th, right? Times 2 is 2/100ths, which reduces to 1/50th, so it cancels, right? So we just get pi centimeters squared
You have to
per
beat it
minute.
too late, otherwise she thinks we're done.
Is that fun?
It's so fun.
I know. Centimeters times centimeters, yeah. And area is squared, so it makes sense that the change in area would be centimeters squared per minute. Come on, Robinson, try and focus on this next question, and I'll forgive you. Are you ready? I know, just watch it. Okay. Here's a medium one. Inherently fun because of triangles. I love triangles. Okay, a 13-foot ladder is leaning against a house when its base starts to slide away. Hopefully you're not on it. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. And the question is, how fast is the top of the ladder sliding down the wall then? Okay, so we can handle this. We've got a house. Oh, I spelled it wrong. And then we've got a ladder leaning against the house. I guess maybe the house is bigger than that, right? Here's my ladder. And what's happening? The ladder has a fixed length, right? It is exactly 13 feet long. And it starts to slide away. And by the time the base is 12 feet from the house, so at the instant when this is 12 feet from the house, when this happens, the rate of the base, should we call this x? This feels good to be x, and that could be y, right? The change in the x, so you would say dx dt is equal to 5 feet per second when x is equal to 12 feet. Okay, it's at that instant. It's changing all the time probably, but that's what it is at that instant. Okay, that's pretty much all the information I'm seeing. Now they want how fast is the top of the ladder sliding down the wall at that instant that x is 12 feet. So what are they looking for? What do we want? How fast is the top of the ladder sliding down the wall? How would you tell that in mathematical terms? What would you call that?
dy dt.
Good. They want dy dt when dx dt equals 5 feet per second and x equals 12 feet. All right? Okay, Robinson, give me an equation that relates all the things that we know.
I don't know.
Okay, so dy dt,
You need one, so the
5 feet, so you have the derivative of 5.
But this is what it's
It's 1/2 based on pi, like to get the area part, but we're not doing that.
No,
Ignore
you're
it.
getting the speed, so it would be
Yeah.
5 feet times the 12 feet, right?
Would it?
Like 12 feet down, it's going 5 feet per second. How many seconds? 12 divided by 5?
Is it just 12 divided by 5?
Okay, that's actually really good. You guys had some good thinking. That's all wrong, but it's really good thinking. First of all, I heard someone say 1/2 base times height. No, I mean, it's okay to be wrong. It's good. It was good because I could hear all y'all talking too. I heard someone say 1/2 base times height. They were just grabbing a formula somewhere out of the air. That's the formula for area of a triangle. Nowhere is area discussed. So while it is a formula related to the triangle, it's not the one I'm looking for. You might, I mean, if you know me, you know which formula I'm talking about when I'm talking about a right triangle. But because there's only one triangle formula that I really care about. What do you think the most important formula is?
Big Daddy.
That's right. So in terms of this particular problem, how would you say it? Would you say maybe x squared plus
Y squared
equals?
C squared 13 squared.
Yeah, and in this case, that 13 is fixed, so you can put that 13 down. But there are problems actually where that's not fixed. Like if there's two airplanes coming together, you know, even that's changing. But here, that's fixed. The ladder's fixed, so you can put the 13 down. Okay, the other thing that you did wrong, Robinson, which was really good, was you plugged in too soon. I think you said something like 12/5, or I mean, you wanted to put those numbers in way too soon, okay? We have to actually first come up with a formula and then differentiate with respect to t and then plug in. So you modeled through your language a lot of the wrong ideas, which is good. It was good because, you know, if you just watch me do it, I do it right every time because I came prepared. All right, so now, can you please, Robinson, differentiate this formula with respect to time?
You're right.
Because 2 the derivative.
Not yet. We don't put the 12 in yet. Somebody said x equals 12. We don't put it in yet. We're going to put it in, but not yet. Because we first have to do the differentiation. The only reason we can put the 13 in is because it's a fixed ladder. This 12 it only occurs at exactly the moment that dx dt is 5 feet per second because it's sliding away.
2x dx dt plus 2y dy dt.
Yes. And then what? Equals what?
And then 26.
Zero.
That's what you just said. And then 0. Why not 169? Yeah, why not?
How about 0? It doesn't matter that you think 13 squared is 26. The derivative of 26 or 169 are both 0. So that's okay, you know, whatever. All right, now we are ready. We are looking for dy dt. So at this point, you can solve for dy dt if you want, or you can plug in at this point and use the numbers and then solve for dy dt, okay? So now we're ready to put that 12 in. See, if we had put that 12 in too early, we would have missed out on our chance to put dx dt in there. Okay? All right, so now we can plug in, and we'll get 2 times the 12 feet times dx dt, which is 5 feet per second. Plus, can anyone tell me what y is? No, we're looking for dy dt. So this is going to be 2 times 12 feet times 5 feet per second plus 2. I don't know what is y, and then I know I'm looking for dy dt equals 0. All right, so $1 million question. At the instant that x is 12, what is y?
5.
There it is. Pythagorean theorem, 5, 12, 13. 169 minus 144 is 25. The square root of 25 is 5. So at the instant that x is 12, y will equal 5. So because we are now looking at the instant, we're going to put that 5 there. Does everybody see where I got that 5 from? Just using the Pythagorean theorem. Okay, and so then this is 12 times 2 times 5 is 120 feet squared per second plus 10 feet dy dt. And all I have to do is solve for dy dt now. So I'm going to move the 120 feet per second over.
Negative 12?
She already did it.
Yes. Second over and divide by the 10 feet, and I do get negative 12 feet per second. That is the related rate. So actually, by me asking you questions, you made a lot of the mistakes that students tend to make, okay? So mistakes are good when you learn from them. So try and kind of really pay attention to this idea that you have to have a general formula. You have to differentiate implicitly with respect to t. Remember, when you differentiate a constant, it is 0, and do not plug in until you're really ready to plug in, okay? And the only reason I could put this 13 in is because that never changed. But do you understand that this base, the distance that you're away, is going to be constantly changing because it keeps sliding, right? So that's just at the instant that it was 5 feet per second was the rate. Okay, now it says, at what rate is the area of the triangle formed by the ladder on the wall and the ground changing then? Okay, so I'm going to just move along here. The area formula, Robinson told us earlier, was 1/2 base times height, which will be 1/2 x times y in this scenario. All right? So we want the rate the area is changing. So we're looking for dA dt. We're going to have to use the product rule here. Okay? So it's going to be 1/2 u times v prime, which will be dy dt, plus u times v prime plus v times u prime. So y times v prime, which is going to be 1/2 dx dt. Everybody okay? Or do you need to see the u and the v thing? You good? Okay, and so then this is kind of crazy. You can take the 1/2 out, so you don't have to keep looking at that. So this is going to be x dy dt plus y dx dt. And you actually know all of these numbers now because you found dy dt in the first part of the problem. So this is 1/2. What are we going to put in for x? 12 feet. Dy dt was negative 12 feet per second. Y we found to be at that instant 5 feet. And dx dt we found to be 5 feet per second. And you should always be checking your units. Do you see that you are going to have feet squared per second? And that's good because that is what area would be changing at. Area is a squared unit. So this is negative 144 and positive 25. And then you take half of that. So you can do that on your calculator, but you should get negative 59.5 feet squared per second. Okay? All right. Gets better. At what rate is the angle between the ladder and the ground changing. All right? Robinson, are you feeling good? Give me a formula that relates the angle theta. 13. And you want the ground changing. So you really don't want your formula to involve y because we're talking about the ground.
Cosine?
Yes. All right. Is that what you were thinking, Robinson? I don't know. Are you there? You're not talking to me anymore?
Cosine theta equals x over 13.
Good. Cosine theta equals x over 13.
Cosine theta equals x over 13.
X over 13.
Oh, 13.
X over 13.
X over 13.
Yeah. All right. And so we want d theta dt. All right. So what is the derivative of cosine theta?
Negative sign.
Negative sine theta d theta dt. Yes? Yes. Is equal to, what's the derivative of x over 13?
1/13.
1/13 dx dt. Very nice. Okay. Now, what is, oops, is that you leaving? Bye, Robinson. Okay. What is the sine of theta? Or so we can solve this for d theta dt, if you want, is equal to 1/13 dx dt divided by negative sine theta. Now, I argue that you actually know all of these at the instant, all right? Because at the instant that x is 5, y is 12, right? And you know dx dt because they told you dx dt. They said it was 5 feet per second, right? In the beginning, dx dt was 5 feet per second. So you'll put 5 in here. Who can tell me what the sine of theta is?
The x12.
Oh, thank you. The x is 12, yes. And the y is 5. And so what is the sine of theta at that instant? Opposite over hypotenuse, right? So it will be 5 over 13. You all with me? So you will have here 1/13. This is 5 feet per second. And then this is just a ratio, so negative 5/13. And so when you multiply this out, you get negative 1. And your feet actually, this is let's see, this is 13 feet right here. So this is feet. So you get nothing per second. You get a unit per second, right? And in terms of angles, that's going to be a radian per second. So that's when it's unitless and you're dealing with angle, it's a radian. Okay? Fun? I don't know. Here's a yucky one. Sand falls from a conveyor belt at the rate of 10 cubic meters per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base diameter. How fast are the height and radius changing when the pile is 4 meters high? Answer in, of course, centimeters per minute. So we have to really mess our brains up because we've got some things with meters and centimeters and all sorts of stuff. All right, so it's like a conveyor belt, like it's some sort of belt, and it's got like little bits of sand on it, and it's falling into a conical pile like this. All right, and we know that it's happening. It says what's happening? The height of the pile is always 3/8 of the base diameter. So I'm going to use R and H. and h is always going to be 3/8 of the diameter, which is here 3/8 of the diameter is twice the radius, so 2r, right? So I put it in terms of radius because they asked for how fast is the radius changing. So this is 3/4 r. So that is a very good thing, because what I have done now is I have described h in terms of r. So if I come up with an equation that involves both r and h, I can replace h with how it's described in terms of r. Does that make sense? Okay, so it says how fast are the height and the radius changing in the pile when it is 4 meters high. So we need some sort of formula dealing with our thing, our shape. Now we are told that the sand falls from the conveyor belt at a rate of 10 cubic meters per minute. So when you see cubic, what unit, what thing or measurement do you think of? Volume. Okay. So does anyone know a formula for volume of a cone? No big deal. You could Google it, but it is 1/3 pi r squared h. Similar to a cylinder, but you take a third. You can prove that in calculus. We'll prove it maybe later. All right. Now, if we want to do first how far if we want dH/dt first, then what we can do is, because we're looking for how fast is the height changing when the pile is exactly 4 meters high, what we can do is we can solve, if we know that h is equal to 3/4 r, we could solve that for r as well. So this implies that r is equal to 4/3 h. Do y'all agree with that? If h is equal to 3/4 r, then r must be equal to 4/3 h. Okay? So I'm going to take that and pop it in right here. So I'm going to get v equals 1/3 pi r squared, which is 4/3 h squared times h. And so then I will get v is equal to 1/3 pi times 16/9 h cubed, which is 16/27 pi h cubed. So then dv dt is equal to, this will be, the 3 comes in front and it'll cancel with that, so that's going to be 16/9 pi h squared dh dt. Everyone okay? Okay, and then do I know anything? Can I plug anything in? I know I'm looking for dH/dt because that's how fast are the height changings. I know h because it's at the instant that it's 4 meters high, right? And I know dv dt, right? Because it's 10 cubic meters per minute. Are y'all with me? Okay. So I can plug in 10 cubic meters per minute for dv dt. I've got 16/9, I've got pi, and I know h is 4 meters squared. And then that's dH dt. So I'm going to do 10 cubic meters per minute. And, all right, this is 16 times 16. So 16 squared with a pi. So that's going to be on the bottom. 16 squared pi is in the denominator. And the 9 is in the top if I were solving for dH dt. Are y'all okay? And this is meters squared. So I am going to end up with meters per minute. Okay, so 16 squared times, let's do, so this 90 over 16 squared pi meters per minute is dH dt. Okay? And I can get this number. Okay, so I'll do 90 divided by, be careful here because you have to put that in parentheses, 16 squared times pi. All right, now this is meters, what was it? 0.1119 meters per minute. So if we wanted to convert that to centimeters per minute, what do we need to do? We need to multiply that by, let's see, there's 100 centimeters in a meter, right? So we want to cancel the meters and end up with centimeters. So we want to cancel the meters and end up with centimeters, and there's 100 centimeters in one. So we're going to multiply this by, we'll move our decimal to the right 2 places. So this is 11.19 centimeters per minute is equal to dH dt. Y'all okay? Now, if you want to do dr dt, then you do the same thing, except that you're going to take this 3/4 r, h equals 3/4 r, and you're going to pop that right in there. And then you go through and work this problem the same way. Okay, so I'll leave that as an exercise for you. Does that sound okay? Or you want to see it? I'm getting nothing. I feel like I'm getting tired bodies. You could do it? Could you do it? Eventually. All right, let's do it. I don't know that you can do it. You seem tired. Okay, so we'll move this and we'll answer this in a second, or we'll answer right now. What are the volumes for the surface area of a sphere? Surface volume and surface area. Volume for a sphere is 4/3 pi r cubed.
Isn't there a sheet for that too?
Probably. And surface area is equal to 4 pi r squared. Surface area is kind of fun. It's the derivative of volume. If you look at it, you can see that. But anyway, let me finish this problem now. So back to problem 5. Number 5, looking for rate of change of the radius. Do y'all need to stand up for a second? Are you with me? All right, so talk me through it. What am I going to do first? What formula am I going to write down? Okay, V equals 1/3 pi r squared h. Now, I want the rate of change of the radius. I need to get rid of that h. So I will replace h with what h is equal to in terms of r, right? H is equal to 3/4 r. So I'm going to come in here and put that in right there. All right, I'm not ready to do that yet. Still just working my formula. Still just making my formula in terms of only R and V. Okay? Still cleaning it up. All right, so this is 1/3 pi times 3/4 R to the third. Right? Because R squared times R. And those 3's cancel. So this is pi over 4 R cubed. Everybody okay? Yes? Okay, so now I'm ready to go. So what is dV dt?
R squared.
There you go, 3 pi r squared over 4 times dr dt. Okay? Now, here's a trick. We know dVdt, right? dVdt is that 10 cubic meters per minute. We're looking for drdt. How do we figure out what R is? Well, we know that R is equal, H is equal to what? 3/4 R, which means that R is equal to 4/3 H, right? And so at the moment that H is 4 meters, because that was you were told, 4 meters high, we can figure out what R is. When H equals 4 meters, R will equal 16/3 of a meter. So I just plug that in there. Okay? So now I can put that in right there. Okay, so this is, was it 10? Yeah, 10 cubic meters per minute. This is 3 pi over 4 times 16/3 squared dr dt. Okay, and so, and this is meters, this is unit here. Okay, so this is 10 cubic meters per minute. You can just divide by all of this junk if you want. 3 pi times you'll have a 3, you'll cancel, you have 1 3 there. So this will be 16 squared pi over 12. Do you see that? Is equal to dr dt. And so you can type that into your calculator and then convert it, and you should get 14.92 centimeters per minute. So I typed it in and then I converted it.
Where did you get the 12
Okay. Pardon?
Is the denominator also squared?
Right, okay, so this is 16 squared and this is 3 squared.
Yeah.
So I went ahead and canceled this 3 with one of these 3s.
Oh, okay.
And then I did 3 times 4, which is 12. I was just trying to clean it before
Yeah.
And then if you're going to type that into your calculator, you have to type this whole thing in like this. I'll show it to you. So you have to do 10 divided by parenthesis 16 squared pi divided by 12. But see, this is a 3 squared, and this is a 1 3. There's 1 3 here, and there's 3 squared here. So it's really, so I still got one left, and that one I multiplied by the 4.
So how come you did?
You with me? I divided it, yeah. Okay, so then this is 0.1492, and that's meters. To make it centimeters, I just moved my decimal to the right 2 places, which gives me 14.92. Oh, I can just feel the passion. Number 7. Mrs. Brooks, we hate these. Okay.
It'll take a while.
Yeah. I don't think there's a ton of them. Okay. There's always a show me an example, so it could be worse. Come on, thing. No, it doesn't.
Need a button, do this for me.
Yeah. No, it doesn't. It's not going to let me. That's it. That's all I get. Okay, one for the faint of heart. Ha 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 ha. This is my joke. It says, in the late 1860s, Adolf Fick, a professor of physiology in the Faculty of Medicine in Würzburg, Germany, developed one of the methods we use today for measuring how much blood your heart pumps in a minute. Your cardiac output as you read this sentence is probably about 7 liters per minute. At rest, it is likely to be a bit under 6 liters per minute. Oh, if you are a trained marathon runner running a marathon, your cardiac output can be as high as 30 liters per minute. Your cardiac output can be calculated with the formula Y equals Q over D, where Q is the number of milliliters of CO2 you exhale in a minute, and D is the difference between the CO2 concentration, which is measured in something per liter, in the blood pumped to the lungs, and the CO2 concentration in the blood returning from the lungs. If Q equals 233 and D equals 97, what? Or, oh, sorry, 97 minus 56, which is 41. I don't know what that unit is. It's
milliliters of CO2 per liter of blood.
oh, milliliters of CO2 per liter of what? Blood. Okay. So equals 5.68, which is fairly close to the 6 liters per minute that most people have at basal conditions. Okay, so suppose that when Q equals 233 and D equals 41, we also know that D is increasing at a rate of 2 units per minute, but that Q remains unchanged. What is happening to the cardiac output? Okay, all right, so do not fret. You have a formula. This problem, while long, is cool because they did give you a formula. You know that Y equals Q over D. And which one's the cardiac output? That's Y. And they're asking for what's happening to the cardiac output. Okay? So they want dy dt, right? So they want dy dt. They gave you dd dt, right? They tell you it's decreasing, that Q is not changing, and that this is your Q and this is your T. So they give you d dt is decreasing, which is, so it's -2, and they tell you that dq dt is unchanged, so it's 0. It has no change, okay? And we know that Q is equal to 233 and D is equal to 41. Okay? Now, to work this one, this is one of those that I like to write like that and then just use the quotient rule, the product rule. Okay, so then dy dt is going to be the derivative of U times V prime. So it's going to be Q times the derivative of that, which is -1 over d squared, right? And then dd dt plus the derivative of the first, which is dq dt, times v, which is d to the -1. Okay? So you can clean this up a little bit. You can say that dy dt is equal to -q over d squared dd dt plus 1 over d dq dt.
If Q is remaining constant, do we really need to do that though?
No, well, sorry. I know, but just for, if it weren't, then we'd have a formula to work with. Okay, now we plug in and you will see that that part's going to fall out. So you get -q, which is -233 over d squared, which is 41 squared, and then this is -2, and then this is 1 over 41, and then of course this is 0, so it is just going to drop out. So you get dy dt is, this is 466 over 41 squared, which is 1681 liters per minute, which is approximately 0.2772 liters per minute. And what that means is that your cardiac output is increasing at that rate. I don't know if that's good or bad, but it is doing it. I thought it was interesting that it was in the 1800s.
Should it be minutes squared?
You're so picky. Minutes squared, you want it squared?
Because it's the rate at which it's increasing, so it should be liters per minute.
Okay.
And since the 41 is squared, it'd be square unit.
41 is our, is a D, which is in liters per minute. See, this, I'm getting in trouble, aren't I? So, yeah, D is, so you're saying this. And Q is also that, right? No, what's the unit on Q? Mil,
D is, Q, both, Q is milliliters per minute, D is milliliters per liter.
per liter. Okay, and then the change, dt is going to be milliliters per liter per minute. That's what you're saying? All right, let me go back in and pop in all my stuff. You're doing a good job. All right, so I'm going to put milliliters per minute here, right? And then I'm going to do milliliters per liter here. Well, they don't cancel because I got a squared. And when, oh wait, and then this -2 is going to be milliliters per liter per minute, right? Okay, so I'm going to have, well, I've got a squared here and there, so there, that cancels. And those cancel, so I do see I'm just seeing liter per minute. Is that right? These liters cancel. Oh, did you say per minute squared? I think he's right. I see a minute squared too. Do y'all? Because we got a minute here and a minute there. Okay, so your cardiac output is increasing. Thank you. At this rate. It seems I wish it was per minute though. Does anybody see how we might be able to get it per minute? It doesn't.
Well, if it's milliliters per liter per minute, you could also, that's just 1 over a minute.
Yeah, thing over a minute. Thing.
Multiplying it.
But you do have, this is 233, was 233 a rate also? Q. Yeah. Oh, in 1 minute, yeah. It is. Okay. All right. So that's it for this section. Thank you for help with the units.